Right, so most of this slide has just been said, but yeah, so my name's Gareth. I work as part of the runtime technology team at IBM, and I've been looking at the performance of Node.js. So what we're going to talk about today then, I'm going to start off with a brief introduction to benchmarking and performance testing. I'm going to look at some of the key challenges, different approaches that you can take to performance testing, and then what to do if you identify a regression and how to find out what it is that's caused that. We're going to look at some of the tools and examples of using those tools on how to benchmark and look at the performance of Node.js. And then finally, I'm going to give a bit of information about what we've been doing in the benchmarking workgroup. So, an introduction to benchmarking then. One of the most important things when benchmarking or performance testing is to change one thing and one thing only between the different runs and the different things that you're comparing. Now, typically, the thing that you change will be whatever it is you're wanting to check the performance of. If you're wanting to check if the latest version of your application code performs the same or better than previous versions, you'll be just comparing the old version of the code with the new one. Likewise, if you're wanting to upgrade to a new version of Node and you're wanting to make sure that your application runs the same or better than it previously did, it would be the copy of Node that you'd be comparing and changing. It's a very easy habit to fall into of trying to change loads of things at once. So pulling in the latest version of the application code and then also upgrading your version of Node, and may as well move everything onto a brand new machine and also pull in the latest versions of all our dependencies. But then if something does go wrong, it's going to be very difficult to try and work out what it is that's causing the issue. It's worth mentioning that performance testing is quite different to functional testing, whereas in functional testing, typically you'll run something a number of times, and if it works, great. With performance testing, there is not any single one answer that you'll get out of your benchmark. And this is one of the key challenges. So no matter how many times you run your benchmark, chances are each time you run it, you will get a slightly different answer. Whether that be you're measuring the startup time, the chance of it starting to the same number of milliseconds each time is fairly small. So one of the things that you need to be aware of is sort of fundamental run-to-run variance. This can sometimes lead to false positives. If you've got a theory about something that's going to happen, so you might think, oh, my new application code is definitely going to run faster. You might just do one run of your old one. Okay, that took 200 milliseconds. Right, my new one, that takes 190. Brilliant, it's faster. Job done. But typically, you'll get a large range of results. So it's very important to ensure that you run your benchmark a good number of times to give you an idea of the sort of expected variance in your scores. It's also something that's worth mentioning that if you go and run, say, 10 times and you find you've got a 15% difference between the lowest and the highest number, then that could well mean that you would find it difficult to measure, say, a regression or an improvement of, say, 5–10%. To be able to measure that sort of thing, you'd need to run it a good number of times. Something that can help try and reduce the variance would be making sure you've got a consistent environment. So each time you run your benchmark or test your application code, it's good to try and have the machine that you're running it on in the same state. One of the things that we do is we try and reboot our machines before we do each run. The longer a machine's been up, you'll find that the performance may change slightly. And whilst it might be quite good to try and keep it as close by keeping it on the same boot, if you then have to reboot your machine, say you've installed a kernel update or something like that, you've then got back to a state that is going to be very difficult to get back into your state that you think you're normally in. So we found that rebooting the machine before each run at least got us back into a position that we could easily recreate. Something else is making sure that the machine is isolated from outside interference. So that could be making sure your co-workers aren't logging into the machine that you're doing your testing on and running things that is taking away all the CPU. If your benchmark also is using network, trying and having a private network, so you make sure that somebody else isn't transferring a big file across the network and affecting your scores. Something else that you can try is interleaving the two things that you're trying to compare. So that would be doing one iteration of your, say, good build and one iteration of the build that you're testing and alternating between good build and the one that you're testing. The final key challenge is jumping to conclusions. It's very easy to, as I said before, to say, oh, I think my recent code change is going to improve startup time. Do one test, find it's improved, good, job done. But actually, you need to carry on and do a good number of runs to make sure that you've got confidence in the data. Two different approaches that you can take towards benchmarking. The first one being micro-benchmarks. These can be quite good for measuring a specific function or API change. For example, creating a new buffer. It's good for comparing key characteristics. However, there are some downsides to micro-benchmarking as well. The first thing is that even if you manage to improve your micro-benchmark so it runs 10 times as fast, that may not actually translate into real-world improvements when you check it into your big application. If it's something that isn't actually called all that often, it may end up that it doesn't make too much difference at all. The second thing, especially where a JIT is involved, such as V8, is you risk not measuring exactly what you think you're measuring. So V8 has an optimizing compiler and JIT that's looking out on ways to improve your code to make it run faster. It may notice that some expensive operation, for example, assigning a variable from some other function, you don't actually ever do anything with that variable, so it might just take that away completely, and you think, brilliant, it's running really fast, but actually, you're not testing what you think you are. The other approach towards benchmarking is a whole system benchmarking. So benchmarking perhaps an expected customer use case or a larger benchmark. For example, something that we use in the community is Acme Air, which is a fictional airline company. And users can simulate creating themselves an account, booking on flights, checking in, all that sort of stuff. This does have downsides as well, as the more you test, the more code that's involved, there's more scope for variability. So you've run a good number of tests and you think you've found a regression. What do you do now? The first thing is to check. Are you sure? Have you definitely not missed something and actually you've measured somebody logging in and running something that's sapping away all your CPU? Have a look at the expected variance. If you've got a variance of 10% and you think you found a 1% regression, you need to be quite sure, otherwise it's going to be very difficult as you go through trying to make changes to detect whether you've fixed it or not. If you're sure that there is a regression, then you need to have a look at what's changed. Is it your application code? Is it Node? Is it that you've upgraded to a different machine? There's a few different things that you can use to try and work out what the cause of the regression is. There's various tools, which we're going to look at in a second. Second one would be just doing a binary search of the code changes between your good and your bad build. That's useful in some situations, maybe not so useful in others. So if we're looking at Node.js, we need to understand that there's a lot of places a regression could come from. It could be perhaps a change to some of the native JavaScript libraries. It could be that you've just upgraded to a new version of V8, a new version of Node that has pulled in a new version of V8. It could be also that that new version of Node has pulled in an OpenSSL security fix, which sometimes can cause performance regressions because you may not have been doing everything that you were supposed to be doing before. It could be a libuv update. It could be that you've pulled in a new dependency or an updated module that has had an adverse effect on your performance. There's some different tools that we can use. So we could use a JavaScript profiler. There's one built into Node through V8. There's also other external packages you can install, for example, Appmetrics. You can also use native system profilers, perf, tprof, oprofile. They're all options. So as an example, this is a micro benchmark that we've been running at IBM, and it simulates creating a buffer from an array of numbers. We go and repeat this operation a large number of times and then run it through a test harness which tries to either get good quality data or until the maximum number of iterations that we've defined. When we were testing the new Node 4.4 release, we found that there was a regression. So the first few lines are from Node 4.3.2, which was the previous release. And we found that we could get 10.6 operations per second. When we upgraded to Node 4.4, we found that went down to 6 operations a second, which is about a 40% regression, so it's a fair amount. As I said before, it may not actually translate into real-world benefit in your big application. Depends how many times you're creating buffers from arrays, but it was something that was worth investigating. So one of the things that we could use would be the V8 profiler. You can just run that by using --prof on your Node command line. It will then go and generate a file called isolate some hex and then -v8.log in your current directory. You can then use the post processor, which is built into Node, by passing --prof -process and then this isolate log that it's created, and it'll get you a load of different bits of output. Appmetrics, as I said before, is another option, installable from npm. You can add lots of different hooks and different monitoring agents, and also include them in your own modules. And if you're wanting to find out anything more about Appmetrics, we've actually got our Appmetrics architect with us here from IBM today. Another option of going and trying and finding the regression, as I said, was binary chop. It's all well and good if you've got a small number of change sets to go through, but if it's a massive change, for example, you've just upgraded from Node 0.8 to Node 6, then there's going to be a lot of changes to go through and try and work out what's caused the regression. Git bisect is an option which could help you if it's in Git, the change that you're looking at. So before I showed you the V8 profiler, so with --prof, the profile at the top here is from Node 4.3.2, and we can see the hottest method is this lazy compile of from object, and it gives us the line number in the native JavaScript library in buffer.js. And we can see that we're spending about 23.9% of the ticks are happening in this lazy compile. When we go to Node 4.4, that jumps up to 47%. So that's certainly something that's worth looking at. So the lazy compile is part of the compilation. So it's not necessarily a regression in from object, it's the compilation that's taking a lot of the ticks. Perf, the system profiler, you can do a similar sort of thing. So there's a massive number of options you can pass, which you can just get from the perf man pages. And by passing in --perf basic prof onto your Node command line, that supplies perf with the V8 symbols so it can match the JITted or compiled code to what it actually was. And again, with this example, we can see 23% of the time in Node 4.3.2 and 46% of the time in Node 4.4. So we're seeing something to do with compilation. So some extra options that we can pass in. Again, these are V8 options that we can pass in straight to Node, is tracing optimizations and also de-optimizations. And this is what happens when we go and do that on Node 4.4. So we can see, first of all, that the profiler spots that from object is a hot method. It's being called a lot of times. So it's very hot and therefore worthy of being compiled. So it goes and compiles that using Crankshaft. It goes and does some further optimizations, completes the optimization, and then straight away goes and de-optimizes it. So there's a good chance that this is what's using some of our time. After an issue and a pull request, it ended up that the problem was in Node 4.4. We'd gone through and changed in all 4 loops, we'd gone and changed the stepper variable to be declared with let rather than var, which the current optimizer has an issue with in V8. So this will be fixed when turbofan becomes the default, but at Node 4.4 it isn't the default. So we went and reverted the change and got the performance back, which was good. The next bit I want to talk about then is what we've been doing in the Node benchmarking workgroup. So the workgroup's goal, or we have a mandate to track and evangelize performance gains between Node releases. So we've been defining use cases, so where is it that people have been using Node, and what are the areas that we can be looking at to try and get as many real-world examples of people using Node so we can make sure we're looking in the right places for any performance regressions. We've identified some benchmarks, but we still have more to identify, and indeed, if you're aware of any, you're more than welcome to come and raise an issue, or even a pull request, come and submit some more benchmarks so we can be running those in the community on regular builds so we can spot any regressions that may be coming in, which means that you don't end up deploying them in production and then having some issues. We've been running and capturing the results, so you can go to benchmarking.nodejs.org, and we've got a set of graphs of the current benchmarks there, and the results tracking Node 0.12, Node 4, Node 6, and also the master branch. We've currently got 13 members, and we have meetings roughly every month, month and a half, something like that. We do the meetings on Google Hangout, so you're more than welcome to either dial and join in or just go onto the YouTube Live and watch the meetings or listen to the meetings. Here are some of the use cases that we've defined so far. So the first one would be back-end API services. So this would be REST or REST-like services, typically over HTTP and public infrastructure. Their main focus would be trying to ensure that they can get good performance over public infrastructure where things such as latency and bandwidth may be a concern. Service-oriented architectures. So this is where you may have an entire function built up into a single API, and there could be different APIs calling on these, typically used to provide private APIs, and there could also be quite a lot of overlapping. The next one would be microservice-based applications, so nimble, low-resource, quick startup apps, and typically these sort of things may also use some different types of networking, so perhaps UDP, to try and get stuff to happen as quickly as possible. And we want to make sure that we can try and track these so that we don't go and regress them in Node. Generating and serving dynamic web page content, so things such as Express, Happy, Koa, React, all this sort of thing. Very popular frameworks. We need to make sure that we've got benchmarks that cover these so we don't go and check in changes that could potentially affect lots and lots of users. Single page applications, so this is typically where the main GUI of an application is served via HTTP request, and then further updates are done over either WebSockets or HTTP2. Agents and data collectors, so monitoring and managing systems, little applications running on systems, keeping an eye without trying to use too many resources. And then finally, small scripts, so a tooling focus, the sort of things that we need to have very quick startup time, low overhead, and also quick to go away again as well, because typically you're going to be starting doing a little bit of work and then going away. So things such as low CPU and low memory usage here are key. And again, you can go and have a look at those in the benchmarking workgroup with a bit more detail. So for all of those use cases, there's a number of metrics that we'd probably be interested in looking at. Consistently low latency, ability to support high concurrency, high throughput, fast startup, shutdown time, restart, and also low resource usage. Benchmarks that we've currently got running in the community. So we've got some that are tracking startup time. We're also looking at the footprint of a small process. Time to require a module, because that's something that lots of people are going to be hitting. We have Acme Air running, which is throughput. We look at the response time and also look at footprint measurements whilst the application's running, because it's all well and good if it's very small. Once the application gets going, most people are going to have quite a bit of a load applied to their application, so we want to make sure that it's not growing out of control. We've also recently checked in a Docker file, so you can go and build your own Docker image, which will compare two versions of Node and then throw out a comparison at the end. So I'd urge you to have a look at that. We've got a number of other benchmarks in progress as well, looking at the performance of URL, and also trying to be running the benchmarks which are in the Node.js build source and actually graphing some of the results from there. As I mentioned before, benchmarking.nodejs.org, we've got lots of graphs like this. This one is where higher is better. So we can see there at the top that the purple and the blue, which are Node 6 and Node Master, are faster than previous releases, which is what we want to see. There's lots more graphs on benchmarking.nodejs.org, so I'd urge you to go and have a look at there. And then finally, how you can get involved. So as I mentioned before, github.com/nodejs/benchmarking. Go and have a look at what's going on. If you think something's missing, go and raise an issue, raise a pull request, come and have a look at what we're talking about. We want to get more people involved, get more benchmarks, and ultimately make sure that we don't regress the performance of Node.js. So thank you very much.